Good morning, everyone. My work is focusing on the internal multiple elimination algorithm. And there are two parts of my presentation. In the first part, I will give the internal multiple elimination algorithm for all reflectors for a 1D Earth. And I will show the strengths and limitations of this elimination algorithm. And in the second part of my presentation, I will show a strategy to address this limitation of the elimination algorithm. In other words, by the end of my second part presentation, you will get an elimination algorithm without limitation. For internal multiple removal, there are different cases if the internal multiples are isolated in the data. The internal multiple attenuation algorithm can predict the correct time and approximate amplitude of the internal multiple, as shown here in the first case. And in this case, we can remove the internal multiple by using the internal multiple attenuation algorithm and the adaptive subtraction. However, the primaries and the internal multiples are often proximal or interfering with each other. As shown in the second case, in this case, internal multiple and the primaries are interfering with each other. In this case, you may want to predict both correct time and the correct amplitude of the internal multiple in order to remove the internal multiple. And my colleague Jin Long Yang have talked about how important this is to predict both correct amplitude and correct time of the internal multiple to remove the internal multiples. And in this case, Dr. Weglein in 2013 proposed a three-pronged strategy dealing with this challenge. What is the three-pronged strategy? The first is to develop prerequisites for the onshore application. And my colleagues have given, several of my colleagues have given different talks yesterday about this topic. And the second prong is to develop ISS internal multiple elimination algorithm to improve the capability of the ISS internal multiple attenuation algorithm. And there are two aspects we can do to improve the capability of the algorithm. First is to remove the artifacts or the sparse events. And this part has been discussed in the previous presentation by my colleague Chao. And my work is focusing on the internal multiple elimination. And the third prong is to develop new adaptive subtraction criteria. And the internal multiple attenuation algorithm is first given by Ruriel AL 1994 and Weglein AL 1997. And there are two aspects we can improve the capability of the algorithm. And the first is to predict the correct amplitude of all the internal multiples. And the second is to remove the sparse events. And for removing the sparse events, Chao AL and Hongliang AL give an algorithm to remove the sparse events in 2012. And for predicting correct amplitude, early ideas was discovered in Ramirez 2005. And my colleague Herrera in 2012 gave an elimination algorithm of first-order internal multiples generated at the shallowest reflector for a 1D normal incidence case. And in this presentation, I'm going to give an internal multiple elimination algorithm for all reflectors for a 1D Earth with offset data. And in this presentation, first I'm going to give a brief review of the internal multiple attenuation algorithm. And I will show the difference between the attenuation, the amplitude difference between the attenuation algorithm and the elimination algorithm is the attenuation factor. And in order to remove the attenuation factor, we can make the attenuation algorithm an elimination algorithm. Here, this equation shows the 1D normal incidence version of the internal multiple attenuation algorithm. And here, the B1 is very closely related to the data. And we put the data into the algorithm and we can predict the internal multiples. And then I will show in a simple two-reflector case to show how we can get the B1 from data and how we can predict the internal multiple. As shown here, here is a two-reflector model. Let's assume a 1D normal incidence plane wave coming in. And for first reflector, it will get a first primary with the reflection at the first reflector. And for the second primary, when it passes through the first reflector, it will get a transmission coefficient, and then reflect from the second reflector with the reflection coefficient. And then going back to the receiver, we will get a another transmission coefficient. And we can have get the reflection data for this 1D normal incidence case. And here's the data. Here's the first primary and the second primary and internal multiples. And we make a water speed migration of this data. This data is only one trace because it's a 1D normal incidence. And with pseudo depths Z1 and Z2, we can get the B1 of Z, which is closely related to the original data. Now the B1 is ready for the internal multiple attenuation algorithm. We put this B1 into the internal multiple attenuation algorithm. We can get the prediction. And we can compare this prediction with the actual first order internal multiples in the data. We can see it can predict correct arrival time. And it has opposite polarity, and it has two more transmission coefficient in the amplitude. And we call this extra transmission coefficient the attenuation factor. And this factor is the difference between the elimination and the attenuation. And the factor is first noted by Weglein and Madsen in 1998. And this picture shows how the algorithm works to predict a first order internal multiple. In this picture, it's still in 1D normal incidence case, so there's it's not a real angle here. It's just a plane wave comes in, a spike plane wave comes in and comes back. Here is and the algorithm, we didn't look into the algorithm to separate the events. We put the entire data into the algorithm. This figure shows how the algorithm works in the algorithm. The algorithm combines those three different sub-events to predict this first order internal multiple. It can predict the correct time of the first order internal multiple. And the amplitude, as we have discussed before, it will have an extra attenuation factor, extra transmission coefficient. And this shows how the algorithm predict a internal multiple generated at the second reflector. And similar as this first order internal multiple generated at the shallowest reflector, we can say it has a attenuation factor, but it has more transmission coefficient. As we can see here, all the extra transmission coefficient are shown here in red, and they are related to the reflection coefficient from the shallowest and down to the generator of the reflector. And we also note that when we predict all the internal multiples at once, for different internal multiples in the prediction, it will have different attenuation factor. And here's the generalization of the attenuation factor, which is shown here in 1D normal incidence case. Here is the AFJ is the attenuation factor for internal multiples generated at the Jth reflector. And we can say when the internal multiples generated at a deeper reflector, the attenuation factor contains more transmission coefficient. And then we'll talk about we'll derive the attenuation factor in a 1D Earth with offset data. Just we have discussed the attenuation factor in 1D normal incidence case. Now let's consider a 2D world, which is XZ. In this world, assume we have a source and a receiver, both located at z equals 0 depth. And we will get a trace for this receiver. And then we can get a short gather, and we can get several short gather. Now the data we have is a 3-dimensional data, which is a function of the source location and receiver location and the time. Now we make a Fourier transform from the data from space-time domain to wave number frequency domain. Wave number frequency domain, and then now the data is in Fourier domain. If you choose a Ks and Kg, it's a plane wave component of the data due to a plane wave incident. And in this world, and then we times the data with the obliquity factor minus 2IQS, and we can get the B1. The B1 now is ready for the internal multiple attenuation algorithm. Now let's assume the Earth is relatively 1D, so the reflectors are horizontal. And in this case, this picture shows, in this case, the data, we can remove one freedom in the data. So the data has only 2 freedom. It's only 2-dimensional. Now we can have a B1 of k omega equals minus 2IQ times d of k omega. And in this example, here shows the first primary in the Fourier domain. And here is the second primary in the Fourier domain. It also has 2 transmission coefficient and a reflection coefficient, but all the transmission coefficient and the reflection coefficient are angle dependent. And here is the first primary generated, shown here in the Fourier domain. And I will not show all the maths to get the attenuation factor here, but we will show the conclusion we have derived. Here's the attenuation factor for 1D Earth with offset data. It's similar like the attenuation factor in 1D normal incidence case, but in here, all the transmission coefficient is angle dependent. It's dependent on the incident angle of the plane wave. And then I will show how to get the internal multiple elimination algorithm. We have discussed that the amplitude difference between the attenuation algorithm and the elimination algorithm is the attenuation factor. So if we can remove the attenuation factor in the attenuation algorithm, we can make the algorithm an elimination algorithm. And at the same time, we want to remove the attenuation factor in terms of the data. And here's a very important point. We want all the attenuation algorithm and the elimination algorithm predict all the internal multiples at once, directly in terms of the data. And the attenuation factor is not a number. The attenuation factor for different internal multiples is predicted is different. So for different multiple predicted by the internal multiple attenuation algorithm, they will have different attenuation factor. And we will remove all the different attenuation factor directly in terms of the data. Then I'll show how we can get the elimination algorithm. And we use a reverse engineering way to remove the attenuation factor and make the attenuation algorithm to be a elimination algorithm. The basic idea is to, let me show you the basic idea. Although we have discussed here, here is an example shows how we can predict a first order internal multiple generated at the second reflector. And I have mentioned that all the transmission coefficients shown here are related to the reflection from the shallowest down to the generator of the reflector. And all the reflection coefficient, all the transmission coefficient, we can say they are related to those reflectors, and those reflectors are related to the second events, the second sub-event in the algorithm. As we can say, the second sub-event in this algorithm contains only information from the shallowest reflector down to the generator. So the basic idea is we want to change the middle integral of the internal multiple attenuation algorithm and make it a new function f. And this function is still in terms of the data, but this function will remove the attenuation factor and make the algorithm an elimination algorithm. Now let me show you how we can construct a middle integral. As we have said that the middle integral here, we want to construct a new function, which in this function we can remove the attenuation factor. The original internal multiple attenuation algorithm, it has B1 in the middle integral, and we want to remove the attenuation factor in the middle integral. So this function should contain two parts. One part is B1, the original integral, and the attenuation factor. And we want to remove the attenuation factor in terms of the data. And then I'll show you how we can get this attenuation factor directly in terms of data. I will not go through all the math here. I will just show you what is happening here. First, all the attenuation factors are related to the transmission coefficient, as we have discussed in the previous slides. And what we have is the data. The data is reflection data. The data contains reflection coefficient. It contains reflection information. So we need to relate all the transmission coefficient to the reflection coefficient. And then we arrange those reflection coefficient into a coupled term of R and R prime. Here R prime is the amplitude of the primaries in the data. As we know the amplitude of the primaries in the data is not directly in the reflection coefficient. We call the amplitude of the primaries in the data R prime, and the real reflection coefficient R is R. And we arrange those we arrange all the attenuation factor into a coupled term of the real reflection coefficient R and the R prime, the amplitude of the primaries in the data. Then we will introduce an intermediate function, intermediate traces here, which is in this G is an ideal trace, and in those traces, the amplitude of the primaries is directly related to the reflection coefficient. And then we are not going to ask you for this G, but we will then, in the second step, we will construct those functions directly in terms of B1. Now we will construct, at first we will construct all the coupled terms by the data B1 and the intermediate function G. And then the second step, we will construct a function G in terms of B1, which is data. After we did all that, I want to go through all the math. After we did all that, we can construct a middle integral f of B1 directly in terms of the data B1. And then I will show how we can achieve this elimination algorithm. As we have discussed in the previous slides. First, if you get a shortcoming, which is d of xt, you make a Fourier transform of the shortcoming, you will get a d of k omega, which is in the wave number frequency domain. And then you times a obliquity factor minus 2IQ, you will get the B1. And first, we'll use this B1 to calculate an intermediate traces, which is which is a function of g. And then we combine this intermediate traces with the original B1, original data. We combine these two functions, we can get a middle integral f function. And then we put the middle integral f function into the original internal multiple attenuation algorithm. Now we can remove the attenuation factor and make the internal multiple attenuation algorithm to be an elimination algorithm. And then we can output the internal multiples with correct time and correct amplitude. Then I'll show two different tests. First test is for 1D normal incidence test, and the second test is for 1D Earth with offset data. In the first test, here's the model. It's a full reflector model, and we can see here. First, we'll test for perfect data, and then we'll test for band-limited data, and then we test for data with white noise. First, we test for perfect data. Here's the input data. Then we'll show the comparison in this red box, and there exist several internal multiples. This picture shows the prediction of the internal multiple attenuation algorithm. The green line shows the input data, and the red line shows the internal multiple attenuation algorithm. Here, this IM212 is a first-order internal multiple generated at the first reflector. And here, IM323 is a first-order internal multiple generated at the second reflector. And there are two more internal multiples, IM213 and IM312, that's generated at the shallowest reflector. And we can say the attenuation algorithm can predict the correct time and approximate the amplitude of these internal multiples. And here's the prediction of the internal multiple elimination algorithm. We can say that in this elimination algorithm, we can predict both correct time and the correct amplitude for all those internal multiples. And here, the IM212 and IM323, they are generated at different reflectors. So the attenuation factor for this two internal multiples are different. But the elimination algorithm remove those different attenuation factors together in the algorithm. And then we test for band-limited data. And with band-limited data, this attenuation algorithm still can predict very good result. And the elimination algorithm still improves the amplitude. And then we test the data with white noise. And the noise, because in this 1D normal incidence test, is only one trace. So the noise for one trace is the worst situation for noise in the data. But we can still say that even with random noise in the data, we can still predict very good result. We can say we can predict good amplitude of the internal multiples. Then the second test, I will show a 1D Earth offset data test for a 2D source and receivers, because we consider for a 2D world, and in 2D world, a point source is in the real world is a line source and line receivers. Here's the model I use. It's the two reflector model, and the source receivers are located at 0 depth. And here, this picture shows the input data in space-time domain. Here's the first primary, the second primary, the internal multiple. And the middle picture shows the prediction of the internal multiple attenuation algorithm. And the red picture shows the internal multiple elimination algorithm. And now we can first look at the zero offset. Here the green line shows the internal multiple attenuation algorithm, and the blue line shows the input data, the internal multiple in the input data, and the red line shows the elimination algorithm. And we can say the elimination algorithm predict very good amplitude of the multiples. And here's another offset at 200 meters. And we can say the elimination algorithm can still predict very good amplitude. And here's another trace at 800 meters. You can see the amplitude is still very good. And again, this go back to the elimination algorithm, and remind you again, we put the input only the data into the algorithm, and we can get the B1. And first we get the intermediate function G, and we combine the B1 and the G, we can get the intermediate, the second integral in the attenuation algorithm. And we put this into the original internal multiple attenuation algorithm, and we can get the elimination algorithm. And we have discussed that the data we have used here is real data. It contains primaries and internal multiples. However, the primaries in the data will provide the elimination capability, and the internal multiples in the data will diminish the capability of this elimination algorithm. And this is the limitation of this elimination algorithm. And I will propose a modified strategy to deal with this issue, this limitation, in my second part. And here's towards our plan for develop internal multiple elimination algorithm. Currently, the elimination algorithm is for we developed is for acoustic 1D Earth and for 2D source and receivers. Also, we have I need to note that the internal multiple attenuation algorithm is model type independent, and it works in acoustic, elastic, and inelastic. As my colleague Jin Wu will discuss in the next presentation. But the current elimination algorithm is only for acoustic 1D Earth. And we will develop the elimination algorithm for 1D Earth with 3D point source and receivers. And then we will test the 3D point source and 1D Earth acoustic algorithm for an elimination algorithm. And my colleague Xinru Lin will give a presentation after my talk about to rearrange the 3D internal multiple attenuation algorithm from Cartesian coordinates into cylindrical coordinates. And her work will help to develop the elimination algorithm for 3D point source and receivers. And then if we test for an elastic model, if it shows added value, we will test it on field data, where the Earth is closely to 1D. And if successful, we will distribute a documented code to sponsors. And also, we will develop a 3D internal multiple elimination algorithm directly from subseries or terms in the inverse scattering series. And here's my second part of my talk. In this part, I will address the limitation I mentioned in the first part. As we have said, the internal multiple elimination algorithm requires the input only the data, the entire data. And the data contains primaries and internal multiples. The primaries in the data will provide an elimination capability. However, the internal multiples in the data will diminish the elimination capability. And then I will propose a strategy to address this limitation. And those strategies benefit from Chao al. 2012 and Hongliang al. 2012. The basic strategy is because the internal multiples in the data will diminish the capability of an elimination algorithm. So if we first use the data plus B1, which is B1 plus B3, B3 is the predicted internal multiple with opposite polarity. So if we use B1 plus B3, we can attenuate the internal multiples in the data. And then we use this data as a new set of data, new input for the internal multiple elimination algorithm. We can address the limitation. And here shows the flow chart and the modified strategy. Here's the original internal multiple elimination strategy. We put the directly data into the algorithm. And then we will change the strategy of the algorithm. We first put the data into the internal multiple attenuation algorithm. We can predict B3. And then we combine B1 and B3. We add them together to get a new set of data. And use this new set of data put into the internal multiple elimination algorithm. We can predict the correct time and the correct amplitude of the internal multiples and address the limitation of the elimination algorithm. And then I'll show a 1D normal incidence numerical test based on well-log velocity data. And the data is offered by Saudi Aramco. And here, this picture shows the data. It's a 34 reflector model. And here's the input data. And because it's a synthetic data, we can separate the first order internal multiples in the data. And we can compare all the internal multiples with the prediction. Here's an overview of the prediction, and I will then show a zoom in of those prediction. We can see here all the blue lines are the internal multiples in the data, and the red lines are the prediction from the attenuation algorithm. And then we can see this picture shows the prediction of the current elimination algorithm, which means we put the data into the elimination algorithm, and we can say the amplitude is improved. And then this picture shows the modified strategy for the elimination algorithm. I mentioned in part 2 in the previous slides, and we use the B1 plus B3 as a new set of data to put into the internal multiple elimination algorithm. We can say the internal multiple prediction is further improved. And this is a test if we input only primaries. In the real data, we cannot do that. Here's a test to show that the primaries in the data can provide the capability of an elimination algorithm. So if we can say in this case we can predict the correct time and the correct amplitude for all the internal multiples. And here's a blow up of the previous results. Here's the prediction of the attenuation algorithm from 2.535 seconds to 2.555 seconds. And we can say the blue line shows the original internal multiples in the data, and the red line shows the prediction from the attenuation algorithm. And this shows the prediction from the current elimination algorithm, which means to input the original data. And we can see the amplitude is further improved. This picture shows a prediction from the modified elimination algorithm, which is we use B1 plus B3 as a new input for the elimination algorithm. We can see the amplitude is further improved. And again, here I will show the strategy for the elimination algorithm. And for this, in order to address the limitation of the current elimination algorithm, I shown in the first part. This is the strategy to address the limitation. We first put the data into the attenuation algorithm and predict B3, and we combine B1 and B3 to predict a new set of data, and use that B1 prime to put into the internal multiple elimination algorithm, so that we can address the limitation of the current elimination algorithm. And we can see, in order to address the limitation algorithm, we didn't need to develop any new algorithm. We just use the current algorithm we have already had. We don't need to develop any new algorithm to address the limitation. And I will thank all the M-OSRP sponsors for encouragement and support for this research. And I will thank all my colleagues in M-OSRP, and I will thank ILO and Saudi Arabian oil company management for providing the velocity model and their encouragement. Thank you.